Hey everyone, today we're going to go through question 88 on LeetCode, merge sorted array. And it's a easy question, but honestly, it's not that easy. And there's many different approaches for it. Like the most naive solutions are easy and they pass. That's probably why it's an easy question. But coming up with like the most optimal solutions are it is not that easy. So I'll quickly chat through all the different approaches and explain runtimes and things like that, and we can cover a lot of content with just this one question. I think this is a really good question. This is why I wanted to take a video of it. So let's see. So you are given two integer arrays, num1 and num2, sorted in non-decreasing order. Non-decreasing order is pretty important, and I'll explain what that is. So we're given two arrays and two integers, m and n, representing the number of elements of nums1 and nums2 respectively. So we're given two arrays here, and then you could see 3 means we have 3 elements here. 3 here means we have 3 elements here. And our goal is to merge the nums1 and nums2 into one single array that's sorted in non-decreasing order. What is non-decreasing order? Let me define the definition here. Non-decreasing order is basically like the arrays in sorted order, but sorted order. But there's two ways that it could be sorted. It could be sorting in strictly increasing or non-decreasing. So for example, if we have an array that's 1, 2, 3, 4, you could see it's strictly increasing because every element is larger than the element to its left. So that's strictly increasing. That's the more strict case. But non-decreasing would be something like this. It's not decreasing, but it's also not increasing. 1, 2, 2. But all of these still fall under sorted order. So when you're thinking of things that are sorted order, there's these two cases. And sometimes you need to take those hints on those questions because it leads to the most optimal solution. For this question, it doesn't really lead to the most optimal solution, but those, just knowing the terminology is good. What else we do? So yeah, so we want to basically combine these elements over here into one single array in sorted order, in non-decreasing order. So you see, if you join these two, you get this. And what it wants us to do is, instead of like creating a new array to store it in, because one solution to this, like pretend we had nums1, nums2. One solution to this is like if we can create a nums3 array, and then we just compare values and take the one that's less than and throw it in there. So this is like the most naive solution would be to, it's still it's still fast as the other solutions, but it adds extra space. But what we would do is we have nums1 and nums2. We just compare the two values, and the one that's, I'll make this a bit bigger. So our goal is to merge it, right, and eventually return a sorted array. So what we could do is just compare, since we know these two arrays are both in sorted order, we know that putting pointers at the start of both of the arrays will lead to the minimum value. So when we're generating this nums3 that's the final output, we just need to compare, need to do comparisons starting from the front of both of nums1 and nums2. So for example, we see, since it's in both of them are already sorted, we could just put pointers at the start, and we know that's the smallest value in each of the arrays. So if we want nums3, this is going to be our final output. If we want to know what the smallest element will be here, we just need to compare nums1 and nums2. So we know 1 is smaller than 2. So we'll throw 1 here, and then we'll move the pointer up here. And then we'll move the pointer in nums3, which is, let's just say this is our output. Right? 2 and 2, we can pretty much pick any, so we'll just pick the one on the top again. Two, 3, we know it's going to be 2 because 2 is smaller than 3, so we put that one. 3, 5, we know it's going to be 3. So we move this one up again. And then since we're at the end of this array, we could just copy over the rest of the other ones from this one. And the reason why, like the key here is that all we need to do is compare starting from the start of each of these arrays, because since they're in sorted order, we know that we have like the smallest elements to compare, and then the smallest elements of either array should be the smallest element in the final array, and then we just keep comparing them. And once we have this output, since they want us to return the final sorted array inside nums1, we just copy it over into nums1. So we just run another for loop that kind of copies everything from the output array into nums1, and yeah, because we don't need to return a value. That's one very naive solution, and I'll quickly show how that works right now. We can actually avoid actually putting it into nums1, but I don't want, but that might complicate it. Like, yeah, what we could also do is create a copy of nums1 here. Nums1 copy over all the elements to nums1, and then use nums1 as the final output array, and then yeah, basically we don't have to do the copy over at the end from output to nums1. That's what it means when it says we need to do everything in place. Where does it say that here? Oh yeah, must be stored inside an array once. Like, it doesn't want us to return anything out this function. So yeah, let me quickly implement that for that solution right there. So let's say, like we said, we're going to create a copy of nums1. We're going to create this copy of nums1. That's how I make a copy. Now we have this copy and this copy. And then we're going to say we're gonna have our pointers. Let's say num1 pointer equals 0. That's this pointer. Then we're gonna do nums2 pointer. That's this other pointer. And then finally, we're gonna have a final copy. Yeah, this pointer will always just keep moving forward, so we could just kind of do a for loop. And what we're going to do is we're going to say for index in range length of nums1. So we're going to be writing into nums1 here. What we're going to do is if let's think this, because the other case we need to cover is if we hit the end of array, but okay, so if nums1, so now I'm comparing nums1 copy, so if that is less than nums2 So if the nums1 copy is less than the nums2 element, then we add that to the nums1. So basically, we're just comparing these two values. Let me annotate this. We're just comparing these two values, and the one that's smaller gets put as the first element here, and then we move our pointer up there. So that's what we'll do here. So we'll say, so if this is smaller, we'll do nums1 index equals nums1 copy, this one. And then now we need to move our pointer up here. Else nums1 index equals nums2. So this is the other case. So if it's less than an equal, we'll switch it. Sorry, I need to zoom. Okay. Okay, so if nums1p is less than that one, we throw it here, and we move this up, and then we move this up. It's the same here. It's less than equal, so we switch them. And then here hits the else condition, and instead we need to swap this one up there. So what we'll do is we'll do nums1 index equals nums2 right here. And then we'll increase this. If the nums1 copy is less than, and then we also need to check the border conditions here. So I think that will, if nums1p is less than getting index out of range. Let's see. Okay, we have to capture this other case. If so, this is the case we're not at the ends of each of the array, because if we're at the ends of this array, like if we're here, like if the index, or if the nums1p is greater than equal to the length of m, then all we're going to do is copy over nums2. Elif nums2p is greater than equal to length of n. We're gonna copy over. There's a lot of conditions here. I'll explain this in a sec if it works. What? Oh shoot. Essentially, I'm trying to implement that algorithm. Okay, nice, it worked. Woo! Lots of conditions there. Oh wow. Okay. Let me explain how that worked. So we have two conditions here, or we have like 4 conditions here. Pretty much what we want to do is Yeah, we created this nums array, but when we get to the end of one array, we just want to continue copying over the rest because it doesn't make, yeah, because it kind of, if you don't copy over the rest, it will lead to a bad state, and I'll show you why it will lead to a bad state. So let's like run through our algorithm again. This is what our algorithm is doing. So we create a copy of nums1 because we just want to write the final result into the original nums1. So we create nums1 copy using 2 pointers, I guess 3 pointers, 1 pointer on the final output nums1, 1 pointer on nums1 copy, and another pointer on nums2. We start comparing nums1 copy against nums2. That's what this piece of code is doing. First, it compares these two elements. It puts the smaller one into the final output. So it'll put 1 there and move it forward. Then it'll compare. Then it'll put 2 there. It'll use the smaller one, and we'll prefer taking from the top array, and it'll take 2. Now here, the smaller one is actually from nums2. So we throw 2 in here, and then we move this forward. Now, we move this forward. Now, we take the smaller one again, which is 3, and we move this forward. But now since we're at the end of nums1 copy, because nums1 copy also contained extra elements so that it could fit the final result, there's nothing for us to compare, right? Or, yeah, there's nothing for us to compare. So all we need to do, since we're at the end of here, is copy over the remaining elements from like whatever one that we have, like the whichever array still has elements left. And that's what these two conditions up here are capturing. So if the pointer is reaching past like the maximum elements of that specific array, then we just copy over the other one. So that's what it's kind of doing, and then it's copying over 5 and 6 from this final one. And then since nums1 is sorted, that's the expected output. So yeah, that's the first solution, or that's like it's like optimal in time in time, but not really in space. So how fast does that algorithm actually take us? If we count everything up, this is O of n time complexity, because as the input size grows, like taking copy of it grows proportionally to the size of that input or the size of nums1. Let's see. Looping through the index of nums1. I guess nums1 is actually a copy. Okay, yeah, since we're just copying nums1, but actually nums1 is the length of m plus n, because it's saying it's the size of both of these arrays combined. So the algorithm here is actually m plus n time complexity. So to make a copy of it, it's going to take that much time. And then what else? For here, this function is also, since we're just looping over the indexes of nums1, it's going to take that much time. And then yeah, here we're just doing a bunch of comparisons. We're not running any loops inside of it at all. We're just doing a bunch of comparisons. And the fastest it's going to take is like, and since the for loop is progressing at every time and only doing a constant amount of operations, it's pretty much only going to take O of n plus n. So the final runtime is O of m plus n plus, it's kind of like in brackets, O m. And if you play around with the math and simplify, you just get an O of m plus n operation. How much space does this actually take? Since we're making a copy of num1, the space is also O of m plus n. So we could actually solve this question without creating this copy, and essentially get the algorithm at O of m plus n. Right now, the time complexity is O of m plus n, but the space is also O of m plus n. In our optimal solution, we could actually get the time to O of m plus n and the space to 1. And how do we do that? It's by reusing the nums1 copy. And this solution is a bit more like convoluted, and I would say it's harder to get to during an interview. But with some practice, you should be able to get to it within the time. So what you do instead is, instead of creating a num1 copy, you just figure out how to modify the specific array so that it could, yeah, let's see. So this is the goal. So we don't want to introduce any new space. We don't want to introduce any new space, so we just want to work with the current like arrays that we have. So how do we do that? Like one solution you might be thinking about is literally just like comparing the two and then using whatever, like comparing these two, and then since this one's smaller, kind of the same algorithm. Since this one's smaller, we just move up this pointer. Since this one's smaller or equal, we just move up this pointer. Since this one's smaller or equal, we or since this one's actually greater than, we do a swap. Since this one's smaller or equal, we do a swap here. Then you'll see that it leads to this weird solution where you get to like pretty much. I tried going down this approach, and what happens is you start to overwrite values in a very, like you start overwriting values, and it's hard to keep track of essentially where, like here's the edge case. We pretty much hit 0 and 0, and then like which one do we swap? I guess maybe we'll know we're at the end, but yeah, it's like, if you like try exploring going through that path of just like starting from the start, and you'll see that like it's not too fruitful. So what I actually like tried doing after is starting at the end of each array. And then having a pointer at this final one. So that way, like, so now we compare which one's the largest out of these two, right? Since nums2 is the largest, we throw it here, 6. So this is like a 3-pointer solution. And then we move this down. Since 5 is the largest, we put it here. And then we move this down. Since 3 is the largest, we move it here. Yeah. We kind of swap it. And then finally, since 3 is larger than 2, we swap it here. And then finally, like when like this back pointer is less than like the initial pointer, we stop. So that you see how since the kind of the intuition behind this solution here, like working from the back, is that you avoid kind of overwriting other elements that you've already written. With a lot of these array questions, that's kind of what happens, and that's the thing I try to look out for when I'm like going through a solution. I'm trying to see like if like there's a consistent algorithm that doesn't overwrite my other results. But this one, it doesn't overwrite because since we're just picking the maximum, once we can, it's kind of like a greedy algorithm. Once we pick 6 here, we know that that's the largest. We'll never have to write there again and then we just move it back. So yeah, that's a quick explanation on that. Let me know if that even makes sense. It's kind of a hard solution to figure out. So what I'll do is I'll start my 3-pointers. I'll have a pointer at the end, which is the length of nums1 minus 1. That gives us this pointer. And then since we're already given pointers at m, we'll have to take m, and then we'll have to minus 1 from it, and n equals, because like for example 3 here will give us this 0, 1, give us this index, and we just need to point it, like m now points here and n now points here. So what is n here? N is 3, and then yeah, okay, cool. And then we said while the end is greater than equal to m. This is m here. This is n here. And this over here is our end variable. And what we do is, yeah, now while n is greater than equal to m, we just start comparing them. We do if nums1 m is greater than or equal to nums2 n, what we'll do is for nums1 at end, if nums1 m is greater than and equal to, we'll throw it there. So since this one's greater than, or if it's greater than or equal to, yeah, we take that one, and then we reduce the count of m minus 1. And we can minus equal. And then we just pretty much do the opposite here for nums2. So if nums2 is actually the greater, we take nums2 n and we reduce that. So on this, let's see. Index out of range. While n is greater than or equal to m. Okay, 1's probably getting to 0 first. Print m n if these are -1. Okay, we have to also handle the case if we reach the end of the array on one of them. So we'll say if m equal to -1, then we just pretty much do this. We copy over n into it because we have nowhere from m to like add anymore. Elif n equal to -1. We add whatever is from the end of nums of m. Yeah, there. Run that code. Print and print m and n, because we're getting to the end of these arrays. M and n, -1, if. While the end What the heck? Why did that work? Why did, when I fixed this condition, it worked? How long is this video? Yeah. Looks like it worked. Let's see. Why did that work? Do I even need this? Okay, we're getting indexed out of bounds. So that's what I'm kind of doing here. If one of them ended, then all I do is just copy over the other one. Ooh. So okay, let's review the algorithm one more time. So what I'm doing here is if one of them reaches the end, then I just stop comparing them. So I stop comparing them. I just copy over the rest of the ones for the rest of the zeros we need to fill in. So yep. So we're kind of running an O of n plus n time. Our space complexity is O of 1 now. And you could see why there's no extra space is because we didn't fill in the other one. And yeah, hopefully that introduces you like how to solve that question. Hopefully I could probably explain it better, but I'll move on to the next question for now and just give me feedback if that wasn't a good explanation, and I'll find ways to make it better. All right, see y'all in the next video.